Let's talk about, is it linear? To be linear means it is going to be a line that is graphed, because inside the word linear is the word line. So let's look here at the graphs first, because this is the easiest to decide if they're linear. Is that a line? No, it is not. That is what you call a parabola. And this is coming from a quadratic equation. So this is not linear. Is this one linear? Of course it is. Is this one linear? 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 Yeah, of course. Let's put a few other examples on here that are not linear. This is an absolute value. And this is my abbreviation. Absolute value. And it looks like a V when you graph it. And this is not linear. Okay? Here's another graph. And is it linear? No, it is not. So just to give you a few other examples of nonlinear functions. Okay, here's another one, and this one is going to look weird. I want to show you this one. Is that linear? No, it's not. Okay, now let's look at the table. Is the table linear? Now, how do you know this? You have to look at the first difference. So the first thing you do to find the first difference is tell me how far apart these are. And it's 1 apart, and it says +1 because the numbers are going up. Now, on this side, make sure you only do the difference between these numbers, these numbers, these numbers, and these numbers one time, because it is the first time you take the difference. So from here to here, I'm going down 3. 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 Okay. So, since all of these numbers match, guess what we can say about this table? It's linear. Alright. So we do this one here. Doop, 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 doop. They're all the same from here to here, from here to here, from here to here. They're going up by 1. Now we look over here. It's going up. No, it's going down by 3. This one is going down by 1. This one is going up by 1. Wow. This one is going up by 3. So is this table linear? Why not? Those numbers don't match. Let's do this one. Going up by 5, going up by 5, going up by 5. Are you sure? -10 to -5, -5 to 0, 0 to 5. All right. Let's go here. They match, so I'm halfway there. So 10 to 4 is going down by 6. 4 to 2 is going down by 2. 2 to 0 is going down by 2. Is this table linear? No, it is not, because these numbers don't match. So this is not a linear table. Now, I wanted to put the points up here because I wanted you to see this is the relation, and this is the relation in a table. You also see that here, because this is the relation, and then this here is the relation in the table. 2, 4, 5, 3, 8, 2, 11, 1. So now let's look here. From here to here, I'm going up by 3. Here to here, I'm going up by 3. Here to here, I'm going up by 3. Let's do this side. From 4 to 3, that's going which way? Down by 1. 3 to 2, that's going down by 1. 2 to 1, that's going down by 1. And what can you say about these numbers and these numbers? These numbers all match. These numbers all match. So this is linear. Okay, let's go here. -1 is going up by 1. 0 goes up by 1. 1 goes up by 1. 2 is going up by 1 to this one. Negative 3 to negative 2 is going up by 1. I hope you didn't say down. Negative 2 to negative 1 is going up by 1, up by 1, up by 1. So do these match themselves? Yes. Do all of these match? Yes. So is this table linear? Yes. Now I know you notice that I'm circling a lot of stuff, but the directions tell me to circle the linear functions below. Okay, now let's talk about these situations. When you're given word problems and you want to know is it linear or not, you have to think about things being one-dimensional or having a consistent change in the information, because that's what it means to be linear, to have a consistent change in the rate of change. What do I mean? Well, let's look here. We've been calling slope pattern for a long time now, and now we're switching over to slope. And so I want you to see how the slope is the same and it follows a pattern. Well, this one here is 1, 2, 3, and this one here is over 1, 2, 3, and then this one here, so that is 3 over 3, which is the same thing as 1. The slope here is 1, 2 over 1, 2. Excuse me, negative 1, because I went down and then right, so negative 1. And then here I'm going down 2, so negative 2, and then right 2, and that's negative 1. So the slope for this piece is the same as the slope for this piece. It's consistent. It's a pattern. Let's look at this one. It's going from here to here. That's up 1 to the right 1, so that's a positive 1. Up 1, positive, over right 1, positive, slope is 1. Try it again. Up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. The pattern is the same, so this is linear. Why am I talking about that? I'm talking about that because you need to understand that having a consistent change of information, a consistent change in the rate, is going to tell me if it is linear or not, okay? Also, being one-dimensional refers to being linear. So let's look at this problem here. Perimeter of a rectangle. The perimeter of a rectangle is one-dimensional, so this would describe linear functions if you had to figure out which one of these situations could possibly be linear. Yes, I can use the perimeter. Let's talk about volume. If you're looking at the volume, does it consistently change? Is it one-dimensional? Oh, no, 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 no. Volume is three-dimensional because you have the length, the width, and the height that you have to use in order to find the volume. Also, if you look at a bowl, okay, and I wanted to know the volume of what's inside of that bowl, what's the volume of it? How much here? Is it going to be the same as how much is here? Of course not. So that's not linear. Okay? Let's talk about cost. Whenever you're talking about the total cost of an item, the total cost of certain things, that is linear only because they charge so much per pound. And it's going to be the same amount for each pound. Okay? So this one would be linear. Cost in 95% of your problems is always going to be linear. The area of the circle. So here's my circle. And here's my radius. And I want to know, is this circle going to be consistent in the distance all the way across, or let's say the area of this. Not distance, but area. So I want to know, is area one-dimensional? No, it's not. It's not. It's not. It's when you're looking in two dimensions. So this is not linear. It has to be one-dimensional. Area is in two-dimensional. And how do I know? Two dimensions. How do I know? Whenever you see an area problem, it will always say square units. And whenever the problem says square, it is not linear. So if it says square, it's not linear. Okay, the person's height above the ground on a Ferris wheel as a function of time. So if I'm on a Ferris wheel, I'm this tall here, then I'm that tall there, and I'm that tall there, and I'm that tall there, I'm that high there. Is the height when I'm going on this Ferris wheel consistent? Of course it's not. So that's not linear. The height of a ball. Well, that kind of looks like this picture. The height of a ball is not consistent. This says cost, so it is consistent. This says cost here, so it is consistent. The height above the ground of a ball thrown up in the air as a function of time. Okay, if I throw a ball in the air, is it going to move the exact same amount of space each minute or each second? Of course not. That's not consistent. So to be linear means to have a consistent amount of changing information. And if that's not happening, it's not linear. So now we get to the fun part. Now earlier I said that one-dimensional is what is linear. So if it's 2 dimensions or 3 dimensions, it's not linear. So if I see a square, it's not linear. If I see a cube, or length with height, 3 dimensions, it's not linear. So I can get rid of those automatically. Do you see any other squares? Ah, good job. Okay, so now let's look at what's left. Which of these problems would give you a line if they were graphed? And so I know a lot of you are probably going to want to say, if I was in the classroom, I could take my calculator and just put it in the graphing screen and check. Well, I want to be able to show you what it's going to be when you're just looking at the equation. So let's look at x, meaning the same thing as x to the first power, one-dimensional. If the exponent is not there, it means there is a 1. And that when that is the highest exponent, it is linear. So, y equals 5x minus 1. This is the only x. It doesn't have a number there, so I know it's a 1. That's one-dimensional, so it is linear. Look for the x. It doesn't have a number on it, so put a 1. That's the highest exponent I see, so it is linear. Now, this one here is the exponent. Should the x be the exponent? No. That's what we call an exponential function, which we will get into later on this year. Okay, there's the x. No number on it. Put a 1. That's the largest exponent. It is a function. Next. Here's the x. There's a 1. That's the largest exponent. I don't see a 2. I don't see a 3. So this is linear. Now, x equals -4 and x equals 2. We're not going to look at that x and put a 1 on it. We're not going to look at that x and put a 1 on it, because you should recognize what that is already. X equals -4 is 1, 2, 3, 4, a vertical line. And x equals -4 is a line. I can call it linear. Now, is it a function? No, it is not a function. It is not a function, but it looks like a line. Is x equals 2 a function? It is not a function, but it is a line. So, let's go back for a minute. It says circle linear functions. So, can I really circle this? No, because it's not a function. It's a line. It's just not a function. So I can't circle those. Alright, so now let's keep going. On here I can put a 1 on the x. And is it are there any other higher exponents than 1? No, so it's linear. And here, well, I don't see. Let's look at this one. Here, let's look at this one. So here's the x. Put a 1 on the exponent. Is there anything higher? No, so it's linear. And what is y equals 1/2? Hopefully you would tell me it's laying down at 1/2. That's a horizontal line. And so that is a function, so I can circle it. This has an x at the bottom. The x should not be at the bottom. This is what you call a rational function. That's not a linear function, so no, that's not linear. You didn't know that. There's no way you would know that. I put it in there so I could mention it. Here, there's my x, put a 1 on it, and it is not a function? No, it is, because that is the highest exponent, that 1 there. Okay, here, y equals x. Here's the x, put a 1, that's the highest, it is linear. Here, there's the x, put a 1 on it, that is the highest, it is linear. Now, do you notice here you don't have an x, but you have y? Well, when y is the only letter there, it will be a function, a linear function. Here you have x and y. The x doesn't have an exponent, put an exponent on it, it is linear. So now when you come to class and your teacher gives you this worksheet, you have it already completed.